So now we have the product rule that gives us rise to the power rule. Now this will take a few more steps than the other ones, but if you recall, the power rule is just if n is a integer, then when we do a power, we're just multiplying u by that power, right? So if, say, u cubed is just u times u times u. So we'll use that idea and the product rule that we already have to get a sense of how to do this rule. So the first case we look at is when n is 1. And so the derivative of u with respect to x is exactly what it is, but we could rewrite it this way. 1 times u to the 0. Notice that that's just a fancy way of writing 1, right? 1 times, so u to the 0 is 1, so this is just a fancy 1. I'm introducing it, though, to see that we'll hold the pattern. So clearly du dx is equal to 1 times du dx. And so just like the rule says, n should be first, and the power should go down by 1. So our power here is 1. We've gone down to 1. So this is kind of a silly case, but yes, du dx is equal to 1 times u to the 0 du dx. Now, if n equals 2, then we need to use the product rule, right? Because then du squared dx is simply derivative of u times u dx. And our product rule that we proved in the previous theorem, so this is du dx times u plus u du dx, which is, I can rearrange this, 2u du dx. And so, just like the rule says it should, the degree in the numerator, or sorry, the degree in the exponent came down to become my coefficient, and the degree of my function went down by 1, from 2 to 1. So let's do it for a few more cases, and we'll see a pattern here, that if n is 3, then du cubed with respect to x. I'll look at this as a product, so this is the derivative of u times u squared dx. Which is, product rule says it's du dx times u squared plus u times du squared dx. This we can't reduce anymore, but this one we just calculated before. So this is equal to du dx u squared plus u times 2u du dx. Now, I've got a u squared here, and when I multiply it here, I get 2u squared, so this becomes 3u squared du dx. And now, what happened? Just like the pattern said in the theorem, that 3, that was my exponent, becomes my coefficient, and the degree of my function goes down by 1. All right, let's do just one more case in case we don't see that you haven't seen the pattern yet. We'll do it for n equals 4, but it should be familiar. So we get, if n equals 4, differential of u to the fourth dx, or the derivative of u to the fourth dx, and I'll write it this way, d of u times u cubed dx, which is equal to the differential of u dx times u cubed plus u times the differential of u cubed dx, which is the first term can't be simplified anymore. But I can, from the previous step, know exactly what the differential of u cubed is. So this is plus, so it's plus u times 3u squared du dx. I've got a u cubed here, and I've got 3 u cubes here. So this is equal to 4u cubed du dx. So I've shown it for 4 numbers. Well, how many positive integers are there? There's a lot. So we go and take advantage of a proof technique called proof by induction. The textbook does a nice job describing that, but we'll just employ it here. So if you want to dig deeper, the textbook explains it. But it goes like this. Let's assume that we've shown that for m, the differential of u to the m with respect to x is equal to m u to the m minus 1 du dx. Right, so we're assuming that we've already shown it, like we just did. We showed it's true for 1, 2, 3, and 4. So in the steps we did, we kept using the previous information, right, to prove that the differential of u to the fourth was 4u cubed. We used the fact that we broke it up into 2 pieces, and we knew already what the previous derivative was. So we're going to start with that assumption that we know what this is already, and we'll calculate what du to the m plus 1. So what the next next exponent power would be, and this is du times u to the m dx, which product rule says this is du dx times u to the m plus u du to the m dx. And now from this assumption, we know what that derivative is. So this is du dx times u to the m plus u times m u to the m minus 1 du dx. This u comes in, increases this power by 1, so they agree. And so we have m plus 1 times u to the m du dx. And so we've shown by our algorithm that we could always get the next power derivative if we know the previous one, and we've shown we can do it 1, 2, 3, and 4. So now this is enough to hopefully convince you, and definitely convinces a mathematician, that this is a valid rule for dealing with powers, at least positive powers.